Here's how to make a best fit linear approximation to your data quickly, whatever. Say, here we go. So say you have some data, you want to approximate it, and you want to find, this is your model, you want to find the coefficient A and B. So you have different measurements, which means that you can write out your system as xi 1 this can be a matrix. This has A, this has B, equal to yi. So, how do you solve for A and B? These are your measurements, like the x's that you know. These you also know. These are your respective measurements. So if we rewrite this equation in matrix form, we can say that this is x, this is the coefficient vector, and this we call y, the y vector. So how do you get C? So just algebraically, you'd like to multiply by the inverse of x and get C equals something. But x is not invertible in this case, since it's not even square. And in general, we can't always do that. So, like, the trick is, if you multiply, how do you make any matrix? How do you go from any matrix to a square matrix? You can multiply by its transpose. So if you multiply both sides of the equation by, by x transposed, you get this. Now that this is square, you can multiply by the inverse and get C equals x transposed x inverse times x transposed y. So that's a matrix, or an operator, whatever you want to call it. This is a vector, and this is a vector, and this is exactly what you're looking for. Now, I haven't explained, you can go check it out for yourself, but this is like the least distance, the minimal distance in the coefficient space. In all the coefficient space, this is the least distance, or the projection, whatever. But this is just how you solve it. So if you have your matrix of measurements, you put it in this form, and you calculate this. You multiply by the vector of the respective measurements, and you get your C, which is just A and B of your model. And you can see I just did it. See, I just did it here.